like to do today is to try to present an overview of some recent work which has been done jointly with Nicola Garofalo, Ashok Petrosian, and Tung To concerning the parabolic Signorini problem, also known as the parabolic thin obstacle problem. And in particular, what I would like to stress is how techniques that were only recently applied to this problem, recently, and I mean the last 7-8 years, have really sparked an interest in the many new results in a problem that was formulated first several decades ago. So the first time the Signorini problem was posed by the person from whom the problem took the name. And Antonio Signorini was an engineer and a physicist, and he was trying to interested in figuring the optimal or equilibrium configuration for an elastic body set to rest on a frictionless rigid surface. And the existence of the solutions and uniqueness was proved by Fichera, who was a student of some sort of Signorini in 1963. It was also Fichera that gave the name to the problem. So this is the picture of what I've just described in words. But the Signorini problem since then has found applications in many, many different fields, optimal control, financial mathematics, osmosis, and I could go on and on and on with applications, but I'm not really concerned about those. Mine will be a theoretical presentation of regularity solutions for the regularity properties for the solution and the free boundary. So the easiest way, and I apologize with those of you, there are many here who are familiar with the problem already, but I'll just try to quickly give an idea of why we formulate the problem the way we do. So, and probably the easiest model to look at is the one of osmosis. So we have a chamber which is divided in two sections by a semi-permeable membrane. The density and the concentration of the solution on the two sides of the membrane is different. So obviously we know that if the membrane is permeable only in one direction, the flow will go from one side to the other until equal pressure is reached on both sides. And so once the pressure equates on both sides of the membrane, the flow will stop. The difficulty of the problem is that we do not know at which point and when exactly the flow will stop or will continue. So let me describe this mathematically from the unilateral side, which means that the membrane, just like in the setting I've described, I'm just looking now at half the chamber. The membrane is going to be one portion of the boundary of a domain omega in Rn. Although the problem is parabolic, let me just focus on a slice of a parabolic cylinder just to make it a little clearer. And then we have our boundary datum on this one portion of the boundary, this one here. And that's given. We have the function u, which is constrained to satisfy the heat equation in the cylinder. And then we have the boundary conditions that I just described before. So basically, when the pressure is bigger than the obstacle, then there's no flow. When the pressure is less or equal than the obstacle, preassigned obstacle, then we have a flow. Now, this constant lambda that you see here depends on the nature of the membrane, and it's directly related to the thickness. Well, what one does in these models is to let the thickness of the membrane go to 0, which corresponds to lambda go to infinity. This would be the parabolic picture in the cylinder. And then what we get is that we have the conditions that we prescribe now this way. We want our solution to be above 5. Phi, remember, is defined only on this portion of the boundary. Then we have the flux, which is always greater or equal than 0, but then we have this compatibility condition. We want either one of them to be 0 at any given time and point in space. So these are known as the Signorini boundary conditions, but again, this is not the original name. Signorini called them the ambiguous boundary conditions for obvious reasons. So there's a slight difference in terminology between the Signorini and the thin obstacle. The situation I've described, when the obstacle is prescribed on a portion of the boundary, it's known as Signorini problem. If instead the obstacle lies on a manifold inside the domain, then it's a more general setting, it's called the thin obstacle problem. But they can be treated very much in the same way. We can also look at the problem from a variational point of view. So the solution to the Signorini problem is a solution similar to the classical obstacle problem to a variational inequality described here, very standard one. Of course, what makes all the difference is the set over which we are minimizing. So we have, again, we constrain the solution to be above the obstacle on the portion M, and we have a prescribed boundary datum and initial datum. So very old results, 1976, the solution existence and uniqueness were proved by Duval and Lyons, and they can be found in their seminal book. Let me discuss briefly the developments in the elliptic case that have really generated a new insight into the problem. So in 2006, Atanassopoulos and Caffarelli were the first one to look at this problem with different eyes, and were able to prove the optimal regularity for the problem. So what optimal means that it's C1 in space and Elder continuous of order 1/2 in time. This is the interior regularity of the solution with under two very substantial assumptions: a flat portion of the boundary and a zero obstacle. I should say that the first regularity result was due in 1979 to, sorry, this is the elliptic case. What I meant here, it's not this is the first derivatives are Elder regular of order 1/2. So what I was saying is that 1979, Caffarelli proved C1 alpha regularity, but not with the optimal alpha. And knowing that C1 1/2 is the optimal regularity makes all the difference in the study of the free boundary, as we will see shortly. And then in 2008, Caffarelli and Salsa, together with Atanassopoulos, proved the fine regularity properties of the free boundary. So they proved that at points which are so-called regular, the free boundary can be expressed as a smooth surface. And in both these papers, a tool became fundamental, and this is the monotonicity of Almgren's frequency function, which is indicated here. So Almgren introduced it in the mid-70s in a completely different context, and what he proved was that this functional here is monotone increasing in R for harmonic functions. And the name comes from the fact, as you can read here, that if you have an harmonic function which is homogeneous of degree kappa, then the value of this functional is exactly kappa. What is Caffarelli and Atanassopoulos and with Salsa then found out is that for solutions to the Signorini problem in the elliptic context, you have the same monotonicity property, which was a quite unexpected fact. So the reason why the monotonicity formula plays an important role is because it gives you a tool to control the blow-ups, which in free boundary problems are one of the main tools that you want to use. So there's a delicate interplay between the monotonicity formula and the nature of the blow-ups, which of course are tailor-made for application to the monotonicity formula I've shown before. So let me just quickly give you in a nutshell why this is true. So basically what you do, you have the blow-ups here, and then you take you want to pass to the limit. So you need some kind of control on the gradients. So you take the L2 norm of the gradients, and because of the way the rescalings have been defined, this is precisely the value of the functional n. Let me go back here. It's precisely the function to the value of n at the radius 1. But then you do an easy change of variable, move from UR to U, and then use the monotonicity to control n of R with n of 1. Now your dependence on R is gone, and so this means that you have uniform boundedness of the gradient in L2 norm. You can extract the sequence and pass to the limit. So there's an interesting connection, and I'm just going to go very quickly on this, between the thin obstacle problem and the fractional Laplacian, the obstacle problem without a thin condition for the fractional Laplacian. And there are interesting results by Silvestre and Caffarelli, Salsa and Silvestre, in which they proved regularity of the solution and boundary regularity. What is interesting in these papers is that they allow the obstacle to be non-zero, which was a non-trivial jump in results. And then there are other points beside the regular points. The points that are not regular have been classified to some extent, and I'll come back to this later, and called singular by Garofalo and Petrosian in 2009, and they used other families of monotonicity formulas to describe the structure of the singular set. So this is all elliptic. Now let's come to the parabolic case. So first of all, what did we know about the regularity of the solution when we started looking at the problem? There have been some results between 1982 and 1996, Atanassopoulos, Uraltseva, and Arkhipova and Uraltseva. And in these results, it is proved that the gradient of the solution is Elder continuous of order alpha in space, alpha over 2 in time, alpha between 0 and 1, with subsequent improvement of this alpha. But that alpha was not precisely determined. And as I mentioned before, knowing the exact value of alpha is crucial in being able to develop the theory any further. And then there was a monotonicity formula, very similar in spirit to Almgren's one, due to Poon. So this is the formulation. So this formula, let me just quickly tell you what the problem of this formula is, that is defined in our n. Whereas typically in the Signorini problem, what you have, you start out with the bounded domain. So this is not immediately applicable. Now, there's a bunch of notations here. I don't expect you to remember them, but just as a rule of thumb, the primes are n-1 dimensional points, double prime n-2. And then when we come here, when I have plus or minus, they're upper or lower, and the primes are one dimension less. And the B's are balls, Q's are cylinders, and S are strips. So first of all, we start out assuming that the manifold, lower dimensional manifold on which the obstacle is prescribed is a straight portion of the boundary. That makes our life easier. And then what we do, we define the class of solutions we're interested in. So this is the parabolic problem I've showed you a few slides before. Heat equation in a positive half cylinder with the boundary condition we have examined before on the thin boundary, parabolic boundary. And also we assume for simplicity that the origin be on the free boundary. Now, there is one assumption here that you do not see, and that's the obstacle being 0. And now I'll convince you, I hope, that this is not really a simplifying assumption. So what did we think when we started looking at the problem? We have a monotonicity formula, which is for functions defined in all of our n. Well, easy enough. You multiply your solution by a cutoff, this will be defined everywhere. There's a problem with that, that you alter the nature of your equation. So now you lose, you lose the right-hand side. You get a non-homogeneous equation. The redeeming feature is that on the right-hand side, you do have some control. So if your obstacle is multi-number, say it's C2, then you know that F is bounded, which is what for most purposes you need. And from this formula here, you can also see that having the obstacle equal to 0 does not really make a difference, because even if you assume that phi is 0, some terms do drop, but some others don't. And so you might as well throw in an obstacle different from 0 anyhow. So let me just recap where we are. So we have a monotonicity formula which is not immediately applicable to our problem. So you multiply by a cutoff, and now you're able to use it to some extent you wish. The problem is that now the monotonicity formula is still not applicable because that's valid for caloric functions, not for solutions to a non-homogeneous equation. So you only have a little shred of hope that even if the functional is not monotone, you have a quasi-monotonicity that is good enough for your purposes. So now I'll try to keep the technicalities to a minimum. The original Poon's formula was defined in terms of these two quantities here. But when you try to prove the monotonicity in our context, these two quantities are not the right one to work with. So in order for our computations to eventually work out, we needed to take Steklov averages. So there's a dependence in time as well, or integration in time. And so this is now the expression for our monotonicity formula. So we found that this functional here, which looks very complicated, there's a lot of noise in it, but this functional is indeed non-decreasing for r between 0 and 1. So let's try to get rid of the noise to give you an idea of why this is still good. Well, we are interested in r going to 0. So if you take r very small, basically this term here becomes not influential. The same goes for this. So if you know that your h of u, which is this functional here, if you knew that your h of u is greater than any power, really, of this 4 minus 2 delta is just is useful in the terms of classification of free boundary points, but if you know that h of u is sufficiently larger than a power of r, then basically this functional here reduces to modulus a constant Poon's 1. So everything else is just basically controls the error terms that are generated by the presence of the right-hand side. So with the monotonicity formula at our disposal, now we can study the homogeneity properties of the blow-ups. And we know that the limit of the functional, sorry, I pushed it too many times. There's a limit as r goes to 0, and this number kappa, it's going to play a crucial role. So at this point, what you do, you kind of follow the path that was laid before us. We define the rescalings pretty much in the same fashion that Athanasopoulos, Caffarelli, and Salsa did. And then you can easily check that this is a solution to a Signorini problem now in a strip with width depending on R. And then you're able to prove that there is convergence, at least in L2 sense of U and the gradient of the blow-ups to a limit, that the limit is a global solution to the same Signorini problem. And it also has an important feature, is parabolic homogeneous of degree kappa. And then we started looking at these values of kappa. And what you find out, similarly to the elliptic case, is that there's a jump in the homogeneity of the blow-ups. So if you confine yourself at kappa between 1 and 2, and for a reason that's long to explain, kappa equals 1 is not an admissible homogeneity because of the regularity of the solutions once more, then you can show that there's only one value of kappa that works, and that's 3/2. And once you know that that value of kappa is 3/2, you can relatively easily figure out what your global solution explicitly is. The proof of this fact, by the way, is based on yet another monotonicity formula. That's the Caffarelli parabolic version of the Al-Caffarelli-Friedman elliptic version, and the study of the eigenvalues, the first eigenvalue for the Erstein-Uhlenbeck operator.
So as you're talking about kappa being less than 2, so kappa equals to 2, is there any
well, that goes into the realm of singular points, and I'll try to touch up on that. So if I just confine myself at the attention between kappa between 1 and 2, then there's only one value, that's 3/2. Then you have all the other values greater or equal than 2. And so then we have the regularity. With this explicit global solution at our disposal, we can prove the optimal regularity of the solutions. So the solutions have gradients which are Helder continuous on order of order 1/2, and in time the regularity is on order 1/4. And when I say the regularity is optimal, it is true as far as the space regularity goes. It is plausible that after knowing additional regularity of the free boundary, one can try to prove further regularity in space, but we have not touched that yet. And the proof is basically a consequence of interior parabolic estimates and estimates on the growth of the solution away from the free boundary. And now we come to the analysis of the free boundary. So the number 3/2 plays an important role once more, because the regular points by definitions are the points for which kappa, the homogeneity of the blow-ups, is 3/2. Now, of course, this is a priori definition, because you don't define them that way. You define them that way because once you work with points at which the homogeneity is 3/2, you find out that around them the free boundary can be written as a graph of a regular function. And so that take the name from that. And this is the result that I will mention. And so what we were able to prove is that if the obstacle is slightly more regular than what you need to, notice that here basically I want the obstacle to be at least C3, and before I told you that I only needed it C2. I'll come back to this in a moment. If 0 is a regular free boundary point, then in a neighborhood of that point, we can express the free boundary as a Lipschitz continuous in space, Helder 1/2 in time function. So it's parabolically Lipschitz. So basically, there's a sketch of the proof here. I don't think I have time to go through it. So let me just point out why we do need a little bit of more information on the obstacle. Basically, because we need to pass to the limit for the derivatives. So we need some kind of convergence for the derivatives of the solution of the blow-ups to the solutions of the limit. And all we had before was an L2 convergence. We need some kind of pointwise convergence. And if you assume a little bit more on the obstacle, then you know a little bit more on your function f, which in turn give you the desired convergence of the rescaling to the blow-up. The regularity we obtained is not optimal. In fact, this is still object of investigation. It was proved, the regularity that we know so far is that this gradient of G is actually Elder continuous, parabolically Elder continuous. And there's a very non-trivial tool that one needs in order to get this kind of small jump in regularity, which is a boundary Harnack principle, which was proved by Petrosian and Shi in 2013. And it is my understanding Petrosian and Shi, together with Koch, are a work in progress on showing that the free boundary is actually smooth. So what about the other kappa? So we know now that when the homogeneity is 3/2, the free boundary points are regular. Then what happens when k is greater or equal than 2? Not much is known. So let me tell you right away that the only case where we know something definite is in the elliptic case n equals 2. Then what we know is that the homogeneity kappa can only be 2m minus 1/2 or 2m. But in any other dimensions, in the elliptic case and in no dimension in the parabolic case, such a characterization is known. So what we do know is that for some of these points, namely the one that have odd homogeneity, we can get some results. So first of all, let's define the singular free boundary points as the ones where the n-dimensional Hausdorff measure is vanishing. And then we subdivide these points again according to the homogeneity of the blow-up at the free boundary point. So these are all the points that have vanishing density, and then we further divide them depending on what value of kappa they have. It's important to study singular points because there are some examples of thin obstacle problems where all free boundary points are singular, and this is one such example. So what is important here is that we were able to characterize the singular free boundary points as the ones of homogeneity 2m. So all the even homogeneities are for singular, so-called singular free boundary points. And also they satisfy an important fact that that their blow-up is a non-zero kappa homogeneous polynomial, which has some additional properties. So what can we say about the singular points? Well, first of all, there's an asymptotic development around them. So basically, they behave essentially as a parabolic homogeneous polynomial of degree kappa. And the proof of this fact is based, you see it here, other monotonicity formulas. So this is something that was this approach was first discovered by Weiss first and by Monod immediately or a couple of years afterwards, that these two monotonicity formula, the one in this slide and the one in the next, give you a powerful way to control the blow-up. So basically, you know that you have a limit, but the limit may be different depending on the subsequence you choose. When you combine, it's essentially actually monotonicity formula that tells you that if you apply this to the blow-ups, then uniqueness becomes an almost straightforward fact. And Monod's formula, in turn, is heavily based on Weiss one. So using a parabolic analog of these two monotonicity formulas, we were able to prove the asymptotic development I showed you before. And finally, we achieve the structure of the singular set. So what we can prove is that the singular set is a countable union of the C1 manifolds. And now I've cheated a little bit here because the structure is more complex than that, in the sense that you have to distinguish the point at which the free boundary can be expressed as a function of both time and space variables, or where instead the time is a function of purely space variables. The behavior is slightly different, but in the end, you basically get that the singular set is rectifiable. And as I mentioned, these are the only known points, but there's still a lot to do in terms of classifying all the other points or disproving that other class of points do exist. Other open problems are to look at the physical problem I started out from, where you do not neglect the thickness of the membrane, but you actually have a condition that it's not homogeneous on the flux. It becomes nonlinear, and so the problem is considerably higher, more difficult. And well, I guess these are just the ingredients of the structure of the singular set, together with the main feature is the asymptotic expansion I had on the board before. And with this, I finish, and thank you very much.
Near the regular points,
Mm-hmm.
the boundary is parabolic for some parabolic norm, is that right? And this, near the regular points,
Yes.
the boundary is Lipschitz.
Yes.
Some parabolic.
It's Lipschitz continuous in space and Helder one, and I mean that was the first result. Now what we know is that it's actually it's C1 alpha.
I know more now.
Yes, that's after the boundary Harnack principle of Petrosian and Xi.
No, if you change a little bit the obstacle, for example, the vector,
Mm-hmm.
Is that portion of the free boundary stable? I mean,
We haven't looked at questions of stability. It's a very interesting problem, but we haven't looked at it. So I don't have an answer.
Just a curiosity,
Mhm.
you have your frequency formula with the hit kernel in hot state.
Yes.
You have to do that Karab. But what if you try with the hit kernel of the domain, like the Neumann hit kernel or the Ziegler hit kernel? I don't know if that works. I don't know. Not using performance.
I think there would be some problems because you get an error anyhow because you don't have the right decay. So I think you would generate an error term anyhow, but I'm not sure.
I have one question myself.
Sure.
So I missed that case with the odd case.
The odd actually it's an admissible homogeneity, but it can be shown again in the elliptic case at 2 dimensions that there are no blow-ups that attain that homogeneity.
Okay.
Yeah.
Because I'm thinking 2D, so if you take z square root of z,
Mm-hmm.
and then z to power, and then
Yes, it's. I think
so
the
branching of the analytic branching.
the solution, the global solution would be, in principle, is the imaginary part of z to the 2n plus 1, something like this, right?
Yeah.
But
And
you
then
can
solution.
yeah, there are no solutions that actually converge to this. It's a contradiction argument. It's in the Garofalo-Petrosian paper.
There's one question. I would like to thank Donatella for all her heroic and also Dorian actually. I've been really doing a lot of great job.
Thank
doing
It was a
program
pleasure.
and organizing the seminars and everything. So thank you both actually.
Oh, sure.